So the least squares problem is basically minimize x in Rn norm of ax minus b whole square, right? So basically I will sometimes write down this as norm of ax minus b, or I'll write down norm of ax minus b whole square. It really doesn't matter. That's the least squares problem basically I'm looking at. So this is the least squares problem. Assumption that we had was columns of A are linearly independent, right? Columns of A are linearly independent. Columns of A are linearly independent. So if the columns of A are linearly independent, then we saw a unique solution x hat, which can be given as A transpose A inverse A transpose B, which I also write as x hat is equal to A dagger B. So this A dagger is basically the pseudo inverse, right? So A transpose A inverse A transpose is basically the pseudo inverse. And because columns of A are linearly independent, I know that the Gram matrix A transpose A is actually invertible. And because it's invertible, I have this. So basically what we saw yesterday was that x hat, which is minimizer of this least squares problem, should satisfy these equations. A transpose A x hat is equal to A transpose B, right? So these equations we saw yesterday, they are called as normal equations. Okay, so these equations are called as normal equations. And today we will see the reason why these equations are called as normal equations. Okay, so what is the reason behind these normal equations? So let us look into this particular thing. Okay, so just to quickly recall column representation, if I call it column representation of the least squares problem. Okay, so we have row representation or row interpretation and column interpretation, right? So the better thing to say is interpretation. Okay, column interpretation of least squares problem. So this column interpretation of least squares problem, what did it say? You look at AX, and what is this AX? This AX is basically x1 A1 plus x2 A2 plus so on so forth xn AN, where these A1 A2 AN are the columns, right? N columns. So A1 ith column of, correct? So you are looking at the linear combination of columns of A, and by minimizing this, by minimizing over x in Rn norm of Ax minus b whole square, what you are really saying is that you are trying to find out that linear combination of columns of A, which is closest to the B. That is what we are trying to find out. So if B actually happens to be in the column span of A, there exists a linear combination x1, x2, xn of columns of A, which will give you exactly the vector B. And in that case, this cost function will evaluate to 0. And that's the solution to your least squares problem. So that is something that we already know. But now what we really have is that possibly this vector B is outside this column space of A. And if the vector B is outside this column space of A, then you have to find out that linear combination of columns of A, which will take you closest to the vector B, right? So that is what is really happening. So if you really see this, so suppose this is actually what you have. Okay, so this okay, so I will probably just do away with the Cartesian axis because it does not really make sense, and I cannot really draw a good diagram here. So suppose this is the subspace. Okay, this is the subspace. What is this subspace? Column space of A. Okay, so column span of A or column space of A. right? So the range in linear algebra you call this range of A also, right? So this is the range of a subspace. So this subspace basically is spanned by columns of A and the vector B. So suppose this is the zero vector here, this is the zero vector here, and vector B possibly lies outside this span. The vector B possibly lies outside this span. Now the question is what is the nearest linear combination? What is the linear combination which is closest to this vector B? So can you tell what it would be geometrically? Can you see and guess? So you think of it, your book, your notebook, whatever you have, you keep your notebook as, so this palm is like the column space of A, and this pen which is coming out from the palm outside the plane is actually like vector B. Then what vector on the plane is closest to B? Geometrically, can you tell?
Projection
So
of B.
projection of B on
Rotating the vector.
Projection. Oh, so why would you rotate? I want to find the vector nearest on the plane, right? So I can have this vector also, which is a linear combination. I can have this vector also, which is a linear combination. But I know what is the best linear combination of columns of A I have. I will take this, which will be giving me this particular fact. What is this fact? So this particular vector, suppose, is such that I get it by x hat linear combination of columns of A. Then Ax hat is the vector on the plane, which is perpendicular to what? What is this vector? Can you tell me? The projection when you take, what is this vector? Do you all agree this vector is residual? Do you agree that this vector, the blue vector, is actually the residual, which is nothing but B minus Ax hat? Or Ax hat minus B, it doesn't matter, whichever way you look at. Is that okay? So whenever the residual is actually perpendicular, to the plane, to the subspace, then the foot of the perpendicular, which is nothing but Ax hat, is actually the closest vector to B. Now you see, you take any linear combination. Okay, so my vector is like this, and you take any linear combination on the plane. So from this tip, unless you have a perpendicular dropped on the plane, that is the closest distance, right? You can go like this, it will make a higher angle, right? It will not be perpendicular, right? The distance will be higher, and so on and so forth. So geometrically, do you understand this concept?
Yes, sir.
I unfortunately is not. I am not able to draw this figure very correctly, but this is what is happening. So what is this really saying? This is really saying that R the residual should be perpendicular to Ax hat. Whenever residual is perpendicular to Ax hat, that means that you have achieved the nearest vector in the linear combination. So perpendicular condition, what does it say? So for example, it in particular means that the residual vector should be perpendicular to all the vectors, all the columns of A, because you take all the columns of A, all those columns of A will be lying inside the plane. If the residual is perpendicular to plane, then it means that it is perpendicular to every vector in the plane. So if you choose the basis of that plane, which is nothing but the columns of A, the residual should be perpendicular to each of these columns of A. Is that okay? And in particular, it is perpendicular to this. So the condition that you get is that columns of A transpose, so every column of A should be perpendicular to this B minus A. So inner product of column of A should be perpendicular. So inner product of one column of A with R should be equal to 0, right? So in particular, A transpose B minus Ax hat should be equal to 0, right? So that is the condition that you get. And what does this really tell you? This tells you that you have A transpose B is equal to A transpose A x hat. And what are these equations? These equations basically are nothing but the normal equations that you get here. A transpose A x hat is equal to A transpose B. Same equations that you get looking at the geometry. And what is this really telling you? This is really telling you that A transpose, so columns of A basically are nothing but the basis of that particular plane, and this residual vector R is in the direction of normal of that plane, is it not? The residual vector R is in the direction of the normal of this plane. So that's why these equations are called as normal equations. Okay, so this perpendicularity condition that you see here, the orthogonality condition that you see here, that the residual should be orthogonal to this particular subspace, the column space or range of A. That's something that is really very important. So that gives rise to these conditions. So this is kind of geometric understanding. So this is sometimes called as orthogonality principle. Okay, so this particular principle is called as orthogonality principle in this case. Okay, so this is something that is very important. This is something that is really very specific to only two norm. The orthogonality word itself comes from the two norm, right? L2. This is the two norm. It comes from the inner product. Even this this particular norm comes out of inner product, right? As you recall, norm of x with its inner product of x with itself is actually two norm of x square, right? So there is a very strong connection of the very strong connection of how the norm is getting created through inner product and this orthogonality principle. Okay, so this is like geometrical interpretation, and this is something that is very natural. So when you talk of distances in space, it is very natural for you to see two norm immediately, right? That because there is concept of angle also attached to that two norm. That is something that is very interesting to see. Okay, so this is a very interesting argument, though this argument is still very hand wavy and can be proved very nicely using the concepts of perpendicular subspaces, but I will not go into that. Okay, so there is a very beautiful theory through complete geometrical interpretation, and you can actually prove that the unique solution exists through geometry also. For that, you need to define something which is called as linear span of columns of L as subspace L, and a perpendicular space, okay, L per another subspace we want to define, and based on these two subspaces you can wonderfully say what is really happening. Okay, and then you make the observation that addition of these two subspaces is actually the entire space. So this particular entire space will be Rm. So it will be Rm, and then you will show that L intersection L perp is 0, and with these two things you will show that x hat is a unique vector, and so on and so forth. Okay, so there is a very beautiful geometrical theory. I mean, you can actually write down the proofs very beautifully, but I'm not going to go into those details. This much of geometrical understanding, I think, is enough. So is this geometry behind the least squares is clear now? So any vector B you see, if it is not in the column span, then you take perpendicular, you just drop perpendicular B onto this plane, and wherever that foot of perpendicular goes, that is Ax hat, right? So you have to find out that linear combination. So B is actually getting projected onto the subspace, and you just solve the system of linear equations Ax hat is equal to B hat exactly in that subspace, right? So how do you solve that system of equations exactly in that subspace? You solve it using these normal equations. So this is going to give you exact solution. So this is like solving in that subspace. Okay, so this is like solving in that subspace. So that is what is really happening. So this is a very beautiful interpretation. One more thing that I want to just mention in passing, though I will not spend too much of time on this at this point of time, maybe possibly little later, is the following. Okay, so what did we say? We said that X does not belong to the column span of A. Okay, so it does not belong to column span of A, or we'll call it range of A. X does not belong to this. Then find X hat. Okay, find X hat such that Ax hat is closest to B, right? So this is basically what we meant in words, and then we converted this into Ax minus B its square. right? So that is what that is. So the concept of
Sir,
closeness, yes.
that should be B does not belong to column space of.
Yeah, sorry, B does not belong. You are right. So B does not belong to column space. Okay. And what did we really mean? What did we really mean? Ax minus B. So the concept of closeness, the quantification of similarity or closeness was in terms of two norms, but it is not necessary that we should measure the closeness or similarity in two norm. I can use it. I can use any vector norm to do this. In particular, I can use one norm. In particular, I can use infinity norm. And what would that mean in terms of residuals? In terms of residuals, so for example, if I minimize Ax minus B infinity norm for all x in Rn, what would that mean? That means that I want to minimize for x in Rn maximum of mod Ri, correct? That is what I want to minimize. So it becomes a min max problem. What is Ri? Ri is Ax minus B, its ith component. That is what Ri is. And once you know this, then what is the infinity norm? Infinity norm of Ax minus B is actually maximum over I mod of Ax minus B, the ith component, right? So you look at all the components of the vector, you look at the absolute values of the components of the vector, and you choose the maximum of those values. And what you are saying, that maximum error, maximum of mod Ri should go down. So if the maximum goes down, then obviously all other errors, all other residuals will also go down, right? So this is another interpretation. I could have very well used infinity norm. The only thing is that if I use infinity norm, then I have to come up with a solution also, right? At the same time, I could have used this minimum x in Rn norm of Ax minus B. It's one norm. I could minimize this, right? So what is this basically? This means that I'm minimizing x in Rn mod of R1 plus so on and so forth. How many residuals are there? N residuals are there, right? So mod of R1 plus mod of R2 plus mod of Rn. So this is our one norm. And in general, for any P norm, I could have done this. So what happens in Ax minus B square is basically x in Rn. What I will basically do is R1 square plus Rn square. That is what I am really doing. So this is something that we are focusing on. That's why least squares, because you have sum of squares and you want to find out least of those squares. But this is least absolute deviation, right? So you want least absolute deviation, or you are trying to do min max problem. So these are also different types in which you could have decided to measure the closeness. Okay, and based on how you decide to measure the closeness, obviously the solution x hat will change. All these interpretations of orthogonality and all also will change. So this is something that you have to understand. So this solution is only when you consider two norm, right? So people have various reasons to look at this particular norms, one norm, infinity norm, and there are some applications around. So we'll probably get to one of those applications, which is compressive sensing, little later in the course of video. Okay, so in that particular case, you'll see that two norm is really not the good thing, but this thing, one norm really plays a role. So there are certain other types of things called as LASSO, LASSO also. Okay, so these are also the type of things where you see these type of problems, but you have different norms coming into the picture. So we will there are applications, but we are focusing on two norms. So I just wanted to bring this to your notice, that the closeness or the distance should not always be two norm. It can be a different norm, different vector norm, and based on what norm you choose, you will have different solution exact to the problem. For us, the norm that we choose is two norm, and hence the solution that we really get is actually exact, which is pseudo inverse into B. Okay. The another thing that I want to make in passing is the following. Okay, so how to solve least squares problem actually. Okay, how to compute the solution to least squares problem, how to compute x hat. Okay, so we know that A transpose A x hat is equal to A transpose B, right? So we know that x hat has to satisfy these normal equations. Okay, unique solution x hat is actually given as A transpose A inverse A transpose B. That is also something that we know, A transpose A inverse A transpose B. But in reality, nobody computes x hat in this particular way. Okay, but x hat will not be computed will not be computed like this. Okay. There are several reasons why x naught will not be computed like this, because first of all, you have to compute A transpose X. So even if you compute A transpose X, you will not compute A transpose A inverse, right? You will use some other decompositions that we had seen, and using those decompositions, you will compute this A transpose, you will solve this system of linear equations. So whenever you see a system of linear equations, even if it is A transpose A, X hat is equal to A transpose B, you do not actually compute A transpose A inverse. You do some decomposition, either LU or you do something like QR and so on and so forth, and you go further. So in particular, suppose A is a matrix which is of the size m by n. If A is a matrix which is of the size m by n, then I can have a QR decomposition of this particular matrix. Okay, I can have a QR decomposition of this particular matrix, and this QR decomposition I can split, right? I can split the QR decomposition into Q, which is m by n, and R, which is n by n. I can split it into this particular form. Okay, so I will remove those columns of Q with the remaining m minus n columns of Q, which do not really matter in this decomposition, right? So I will take this short QR, this truncated QR decomposition, and we all know that A transpose A inverse A transpose is actually Q transpose and R inverse, right? So you can actually see this calculation very easily. R inverse Q transpose. We have actually shown this. Pseudo inverse can be written in this particular format. So if this is what we really have, then X hat is actually nothing but R inverse Q transpose B. But do we really do R inverse also? No. We take R here. R X hat is equal to Q transpose B. So basically what we are doing, we are solving this by back substitution, right? And back substitution will happen after you do QR decomposition. And when you do QR decomposition, do you really need to build the entire Q? No, you do not really need to build the entire Q. You can do it step by step and just convert this matrix A into this tall matrix A into this matrix R, right? So Q transpose will go on the other side, and step by step you can calculate. So the calculation, how do you really compute X transpose? You do not really you do not really compute the pseudo inverse A transpose A inverse A transpose. It's not explicitly computed. Through QR decomposition only we will build and we will solve this system of equations. We'll see how we can solve it through SVD also when we learn singular value decomposition. We will see how through SVD also we can solve the system of linear equations. Okay, so this is something that is really very important. And one more thing, I think I can have that example. Let me think. So suppose I have my matrix A like this, 1 0 0 1, and maybe 0 epsilon. If I take it like this, then can you tell me what is A transpose A? 1 0 0 0 1 epsilon, 1 0 0 0 1 epsilon. Can you tell me what is A transpose A? So what is this A transpose A? Can you tell me? Okay, so maybe if I take epsilon 1, 1. Okay, so this example I was having it in my mind, now it's skipping. So okay, so what I'm trying to illustrate here is that given a matrix A, if you compute A transpose A, then computation of A transpose A also is a little dangerous operation. Okay, it is a little dangerous operation. You do not want to get into doing this. Okay, so I'm trying to construct an example. I had it constructed. I actually forgot. It's not a good thing, but so 1 0 0 1 epsilon. What is this product? Can you tell quickly?
1 0 0 epsilon square.
It's not 1 plus epsilon square, right?
Yes, sir.
It will be 1
Plus
plus
epsilon
epsilon, right? So no, I don't want this also. So
But sir, then the A originally should be 0, 1 epsilon. Okay,
no,
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 fine, fine. Yes, sir.
I had this example. Worked out, and okay. So let me remember this example and get back to you. I had this example worked out. So the column should be almost linearly dependent in A. Then you have a trouble in A transpose. That's what we want to create. Okay, you have columns almost linearly dependent. 1, 1, 1, 1 plus epsilon and 0, 0. Suppose A is like this, then what is A transpose A? This is not the example I had, but this is one last time I'm going to attempt this, otherwise I'll move further. So what is this product? It will come something like this, no? So no, this is not the example. Just forget it. I will give that example once again, and I will show you why you should not do A transpose A also. Okay. So given a matrix A, given a matrix A, we should avoid computation A transpose A as well. Okay, so why we should do that, we will see. Okay, I'll give that example. Problem case, where is the problem? The problem case is when matrix A has almost linearly dependent columns. Okay, if that really happens, then A transpose A in the precision with which you are working actually becomes a singular matrix. So theoretically, the matrix A inverse A is not A transpose A is invertible, but practically because of the finite precision of the matrix that you are working with, it becomes what you say in non-invertible, right? Singular, and you cannot really solve the system of equations in that particular case. So there are problems with computing A transpose A also. So generally people avoid computing A transpose A also. Unless they know that such a problem is not going to arise, they will not compute A transpose. So that's why generally you will not even construct the normal equations. From the matrix A itself, you will compute the QR decomposition, and using this particular approach, the one which we had seen earlier, you can actually solve the least squares problem. Okay, so that is something that is I wanted to emphasize. So QR decomposition is one of the best ways, most reliable ways computationally to compute the solution of the least squares problem. Okay, so let us move further. Okay, so any doubt about these things? I will give that example why A transpose A is bad. I'll give that example. But any other doubts about this so far? This discussion we had? Okay, so in that case, I think we can move further and we can kind of look into this particular problem, least squares data fitting. Okay, so this is something, least squares data fitting. Then we will try to see least squares classification. So in the classification also we'll look at binary and multiples. Okay. So this is something that we want to look at. So can we do, can we use least squares? Can we use least squares to do data fitting, classification, this binary and multi-class and things like that? Okay, so that is something that we want to look at. So it's application of obviously what we have done so far. So we will see what is going to happen. Okay, so for example, there is a function f. Okay, there is a function f from Rn to R. Okay, and this function f from Rn to R is such that it explains the relationship between a vector x belonging to Rn and a scalar y nicely through this particular function y is equal to f of x. Okay, so that is something that we know. Okay, so these variables x are called as independent variables. So these are called as independent variables, and this variable is called as response variable. Okay. And this relationship y is equal to fx is something that is well defined already there. The only thing is that we do not know this particular f. Okay, the only thing is that we do not know this particular f, and what we want to do, we want to guess this function f, or we want to find this function f, we want to find this relationship f. And how do we find this relationship f? We find this relationship f with respect to some data. Okay, so I am given some data, some observations are there, some examples or some samples or some measurements, whichever words you want to call them. So that is what is given. So what is given? So I will denote it as x1, x2 up to xn. Okay, so all these are actually vectors in Rn. Okay, so capital N number of things, and corresponding to this I am given these observations y1, y2 up to yn, right? So actually, sometimes we'll call x1, y1 to be xi, yi. Let us say this is the data pair. Okay, this is the measurement pair or data pair or observation pair. So corresponding to these values of x, this is the value of y, right? So that is what we have. And xij will be the jth value of ith observation. Okay, so that is what I'll be, that is how I will find. So you have that ith observation. So the superscripts in the bracket 1, 2 up to n, they are denoting how many number of data points, the number of data points, and this xi, yi is data pair. So these xi, yi's are actually here. Okay, so these are these xi and yi's I am looking at. So I am looking at x1 and corresponding value of the response variable. I'm looking at another instance or another example or another observation of independent variable x2 and seeing what is the corresponding value of the response variable y2. So now what is it that I have with me? What is it that I have with me is this particular data set. So this is the data set that is with me, and I want to find out the functional relationship between x and y. That is the problem, right? That is the classic modeling problem that I have with me, and that is what we want to do. So what is a model? So what we really want to do, we will form a model or the relationship between x and y. So form a model to describe, find a model to describe the relationship between x and y. Okay, that is what I want to do, and I will have this particular model. So I will say y is roughly approximately equal to f hat x. Okay, so this f hat is actually the model. So where f hat from Rn to R is the model, So this is the function. So this particular function will be called as model. Okay, and what is the objective? The objective is that we want to find that model. Okay, and what are the types of models that we can look at? Okay, so the model that we will focus on is linear in parameters model. Okay, so the model that we will focus on is linear in parameters model. So typically what happens is, though I do not know this function f exactly, I may know the form of the function. Okay, so what I really do is that based on that prior knowledge or whatever you want to call, what I will do is I will write down f hat, the model that I'm trying to build, f hat x. So I will choose some basis functions, okay, or feature mappings, okay. So f hat x I will express as alpha 1 f1x plus alpha 2 f2x plus so on and so forth, alpha p fpx, okay. So alpha p fp, okay. So that is what I'm. So f1 f2 fp are where f1 f2 fp, so where fi from rn to r again, fi from rn to r again are basis functions, okay. Basis functions in language of mathematics, or sometimes they are also called as feature mappings, okay, or they are called as feature mappings. So what is really happening here? What is really happening here is I am expressing my model f hat as a linear combination of functions f1, f2, fp. Okay, that is what I am really looking at, and this basis functions is something that I choose. So depending on application, depending on your experience, and depending upon your expertise, you will decide what these f1 f2 fp functions are, okay. So we'll choose them in such a way that f hat will closely resemble f on the data set that we are looking at, okay. So that is what we will do. So the thing is that clearly for a fixed x, in Rn, f hat is a linear function in parameters alpha 1 up to alpha p, right? So in the parameter vector alpha 1 up to alpha p, it's a linear function, right, for a fixed x. That's why this particular model is called as linear in parameters, right? So linear in parameters because you have alpha 1 up to alpha p, this vector. You can write this function f hat as inner product of this with f1x up to fpx, right? So f hat can be written as an inner product. So if you can write a function as an inner product, then it's a linear function, right? We have already seen this. So in alpha 1, alpha 2, alpha p, the parameter vector, this particular thing is a linear function, right? So that is why this is called as linear in parameters model. So what is the objective now? So f1, f2, fp are also fixed. So they are also already chosen. They are also fixed now. Then what are unknowns? The unknowns are alpha 1, alpha 2, alpha p. So once you fix f1, f2, fp, what are unknowns? Unknowns are alpha 1, alpha 2, alpha p. They are the parameters. And you want to find out the parameters alpha 1, alpha 2, alpha p in such a way that the model f hat will be very closely resembling with the model f on the given data set, right? So now we have to quantify what do we mean by this model f hat resembles with the true function f on the data set, right? So that is something that we want to look at, and that can be understood from prediction, okay? Yes.
So to go back, so the F1, F2, these represent the feature values, isn't it?
They are basis
What,
functions
what
for the time being. They are called as feature mappings, but they are basically the basis functions. You will write your model f hat as a linear combination of these things. That's what we basically mean.
Okay. I mean, my
Sir,
question was, like, are they the observe? I mean, in the A matrix, they are the columns. So basically, these are the observations.
So
So,
we'll come to that. We'll come to that. You wait for two minutes. You wait. You will see what these are. How you can relate it
okay,
with a matrix. It will come. Just wait for 2 minutes.
so,
Yes, Ravi, you have something to say?
sir, why is Fi being mapped to R?
Because you are looking at the linear combination and f hat is mapped to R, no? And the reason why f hat is mapped to R is because f is also mapped to R. So given a n dimensional vector, which are consisting of independent observations, this is only a single value y, no? This is a real number. Is it not?
Yes, sir. Yes, sir. So it depends on basically the type of y. It should be
Yeah.
mapped to the type of y.
Yeah, correct. So we are only looking at real numbers values. Real valued functions is what we are looking at. So that's why it will go to R. If this y were like k dimensional vector, then you have to do a k dimensional thing. So everything will be k dimensional.
Yes, sir. I got it.
So right now it's k is equal to 1. So that's why it is not 2. And the thing that how well this f hat matches with f on the given data set, that we will quantify by prediction error. So what do we want to do? Our objective is to choose the model f hat so that it is consistent with the data. That is yi, okay, the ith observation is roughly same to f of xi, right? F hat of xi for I is equal to 1 to n. Correct? So on all the data points, n number of data points that we have, f hat should be such that yi, so this is the observed value of the response variable. This is the input or the independent variables that are given to us. When you evaluate x with respect to f hat, when f hat is evaluated at this particular point xi, you will get certain value of the evaluation. That value should be approximately equal to yi. That is the requirement that we have, right? So let us denote this predicted value as yi hat. Okay, so let us call this as yi hat. So yi hat is basically f hat xi. Correct? Yi hat is basically f hat of xi. Then what do we want? The residual term. So the residual that we define, Ri. So Ri is basically yi minus yi hat. Correct? So this is what the residual is. And what do we want? We want this residual to be as small as possible, right? So we want this residual to be as small as possible. So this is something that we want. And I will just introduce the vector notation. Okay, so I will just introduce the vector notation of these things. So in vector notation, so these are all scalars. So in vector notation, what do we have? I will just denote by yd. Okay, so yd is the vector notation of y1 up to y capital N. Okay, so these are the observed values. So this is the vector. Then y hat d is actually equal to y hat y1 up to y hat yn. Okay, so it is this vector. And rd, the residual, is basically y1 minus y hat of 1, this vector, so on and so forth, yn minus y hat of n, this vector, right? So in the vector notation, I will have these things, right? So this is what we have. So clearly yd, y hat d, rd, they are all vectors in R capital N, right? So they are all vectors in R capital N. And what is it that I would really like to do when I have this particular vector rd? I will like this vector rd to be as close to 0 as possible, right? I will like this vector rd to be as close to 0 as possible. So in general, what will I have? I will try to minimize some norm of this vector rd, and based on the discussion that we have had so far, the obvious choice for us at this point of time to minimize the norm will be the 2 norm, right? So I will do least squares model fitting. Okay, so what I will do is I will do least squares model fitting. In that least squares model fitting, what will I do? I will try to find out this alpha 1, alpha 2, alpha p in such a way that this 2 norm of the residual vector, is actually as small as possible. Okay, so this is what I'll have. Now, so minimize this, and this minimization will obviously occur over these parameters. Okay, so minimization will occur over these parameters alpha 1, alpha 2 up to alpha p. Okay, so so what I am going to do now, is express these things. Okay, express y hat of I, the ith prediction. So this ith prediction, suppose if I write down as a I1 theta 1 plus so on so forth plus a I p theta p. Okay, I is equal to 1, 2 up to capital N. Okay, so this is what I do. Then clearly I have to define what is this AIPs are, where Aij, what is Aij? Aij is equal to actually the function fj. So you will have this function fj, and you will evaluate it at this particular point xi for I is equal to 1, 2 up to n, and j is equal to 1, 2 up to p. There are p basis vectors, so this is what you do. So aij will be equal to fj evaluated at xi. So clearly the matrix A, which is the matrix of these aij things, will be a matrix of the size n by p. Do you all agree that it will be a matrix of size n by p? Kaushik, do you see how the matrix A now is coming into the picture?
Yes, sir. Yes, it's clear.
So this is how my matrix A is coming into the picture. And if you understand this matrix A, then in the vector notation, what do I have? Matrix vector notation. I have this y hat d. That means the predictions, which is the vector of all these y1 hat, y2 hat, y3 hat, is actually equal to this matrix A, which is the matrix Aij, which is basically evaluation of basis functions at the data points, into this vector alpha 1 up to alpha p, the parameter vector. This is what I have. And now what do I want? I want to find out this alpha 1, alpha 2, alpha p such that this vector is as close to y hat. So this vector, which is nothing but y hat d, is as close to yd as possible, right? So this is what I really want. So if you see, what is this residual sum of squares? So the residual sum of squares is basically yd minus y hat d, correct? And what is this equal to? Yd minus a into alpha. So I'll just write down alpha. So where alpha is actually equal to alpha 1 up to alpha p. If p dimensional vector alpha 1 up to alpha p I take, then this is what I have, which is basically same as a alpha minus yd, right? And what do we want to do? We want to minimize this RD sum of squares with respect to alpha 1 up to alpha p is same as you are minimizing with respect to alpha 1 up to alpha p norm of a alpha minus yd whole square. And this is the least squares problem that we had just seen. The least squares problem, which will give me solution alpha is equal to a transpose a inverse a transpose yd, which is same as a pseudo inverse yd, right? So that is the solution of the parameters that I'll get. Once I know the parameters, I know the model, right? Once I know the parameters, this alpha 1, alpha 2 up to alpha p, then I know the model because f1, f2, fp are known to me. Then I know what is f hat, right? So that is what I know. So finding out that model f hat is something that I started with. So I assumed a particular form of the model f hat, which is nothing but alpha 1 f1 plus alpha 2 f2 plus alpha p fp. Then once I had this particular form, then I defined residual. I defined residual, and based on residual, I decided which norm I want to use. And based on which norm I want to use, what did I say? I said that find out these parameters alpha 1, alpha 2, alpha p for me in such a way that f hat, the model that I have, matches with the data that I have observed, which is xi, yi pairs, as closely as possible. So that is what this cost function is really telling, right? So this is the row interpretation of least squares problem that we have seen. You remember that in the row interpretation of least squares problem, this is what we had seen. So this row interpretation actually helps us to construct the cost function. And once we construct the cost function, then you have the expression for alpha, the solution here. So the only thing is that I have written down the solution directly as A transpose A inverse A transpose YD. That is provided A matrix is actually full column rank, right? So we had solved the least squares problem, and in the least squares problem we had seen that the solution exists and is unique only when the columns of A are linearly independent. But here, how can I guarantee that the columns of A are linearly independent? How can I guarantee that? How is it guaranteed that these columns are linearly? Because if the columns of A are not linearly independent, then I am in trouble. No? Any thoughts on why these columns are linearly independent?
The FIs are basically basis, so and they are the columns.
Yeah, so they are basis. So what does that mean that they are basis? So basically what we mean is that no function fi can be linearly redundant on the other functions, if other remaining functions, right? So if this matrix A has linearly dependent columns, if this matrix A has linearly dependent columns, if A has linearly dependent columns, what does that mean?
So that two functions essentially map the set of xi's to similar yi's.
Correct. So A has linearly dependent columns. Then what does it mean? It means that one of the column. So let us assume the last one. Without loss of generality, can be expressed as a linear combination of the remaining columns. And what does that mean? That means that on the given data set, because you have evaluated the functions fi on the given data set x1, x2 up to x capital N, right? So that's what you have done. So on that observed data set x1, x2, xn, the pth basis function fp is linearly deductible. You can find out fp as a linear combination of first p minus 1 functions, right? So that means that this function fp is not giving you any new information as far as the observed data set is concerned. Do you agree? So that function is really not important to us. Just throw that function out, right? Because that is not adding any more information that we would not have obtained from the functions f1, f2 up to fp minus 1. Of course, when I am saying this, I am saying it the information by linear combinations of the functions f1, f2, fp minus 1. Okay, so we are talking in terms of linear combinations, and the reason why we are talking in terms of linear combinations is because our model is linear in parameters. Okay, because the model is linear in parameters, what we are interested in is only the linear relationships amongst the model f1, f2 up to fp. So if one of the functions, say for example fp, you can write down as linear combination of the remaining functions f1, f2 up to fp minus 1, then fp is not giving you any additional information. So any additional information in the bracket with respect to linear combinations other than f1, f2 up to fp minus 1. So we don't want that function. We don't want the redundancy in the basis functions, right? So that is something that we already have to guarantee, right? So with this guarantee that there is no linear redundancy amongst the basis functions, that is something that basis functions will have as a property within themselves, that there is no linear redundancy, the columns of A will always be linearly independent. If the columns of A are not linearly independent, that means that one basis function is linearly redundant from the remaining basis functions and hence can be skipped, right? Hence can be thrown out. You don't want that function to be. Is that okay? So this is what this data fitting is really telling you. Okay, so let us quickly see. So there are some terms that I think introduced in some of the video lectures that I had shared with you. So just to give the idea, so this particular norm yd minus a alpha hat. Okay, so if alpha hat is the solution divided by a total number of observations. So this is called as mean square error. Okay, so this is called as mean square error. So let me still use alpha, mean square error. And when we are minimizing this RD square, basically what we have is that alpha hat which minimizes this function, right? So for alpha hat, this mean square error is minimum. So the alpha hat, the estimate or the value, optimal value, is the value which is obtained by minimizing the mean square error. So it is a minimum mean square error estimate that we are actually having for the model parameters. Okay, so that is what we have. And I think there was something which was called as RMS also, right? So root mean square error. So square root of this is called as root mean square error. Okay, root mean square or RMS. Okay, so typically what people would like to do is that they will say we want to minimize the root mean square error. So when you want to minimize the root mean square error, this is the function of RD. This is the function of RD that you are really trying to minimize, right? So typically here the function of RD that we looked at in least squares is RD square, the two norm. Basically that is same as looking at mean square error, or it is still same as root mean square error. But people may have different choices. Those different choices will lead to different loss functions as you call, right? So our loss function is root mean square error. We'll look at the root mean square error and we will see. In general, some function phi of RD may be used to determine how closely the model f hat matches the data xi yi I is equal to 1 to up to. So something similar to what we had. Like you can look at one norm, you can look at infinity norm, you can look at various other things based on what these things are, right? So phi of RD is a function, any arbitrary function. For us, this phi of RD is basically root mean square of RD, right? Root mean square of RD, which is nothing but square root of YD minus A alpha divided by capital. That is what we have. Okay, so this is the phi RD for us, and this will give rise to least squares estimate of alpha, the model parameters. Okay, so that is what we have. So this is something that we are looking at. Okay, so Is this clear how the data fitting is really going to happen? Okay, so if that is clear, then one very interesting thing. Okay, so least squares fit on a constant. Okay, so this is something that is really very interesting, and I think those who have taken second year probability statistics course, in that course they would have seen this already. Okay, so this is something very interesting. Okay, so those who do not know these concepts can see this. Very interesting. So what we are going to do, we are going to take p is equal to 1. Okay, so when p is equal to 1, you are only looking at one basis function, and what I'm really going to do is that this f1x is actually going to be equal to 1 for every x in Rn. Okay, so what I'm really saying is that this is my constant function 1. Okay, this is my constant function. So in this case, the model f hat is actually constant. Correct? In this case, the model f hat is constant because you have only one basis function. So what is f hat? Basically, f hat will be equal to alpha into f1, which is nothing but alpha into 1, right? So model f hat is actually equal to alpha, which is a constant. So what do we want to do? We want to compute this alpha, right? So I will denote it as alpha 1 just to make sure that you do not confuse with this alpha, which is a vector. Okay, so let us see that alpha. So what is the matrix A? So the matrix A is n cross P. So that matrix A, which is n cross P, is actually n by 1 matrix, and this matrix is of all ones, right? So this is of all ones, n cross 1, right? So this is typically denoted as 1n, right? Vector with this. And what is the estimate for model now? So alpha 1 hat, what is this? So we know this A transpose A inverse A transpose into YD, correct? A transpose YD. Where what is YD? Where YD is actually the vector of Y1 up to Y capital N observations, correct? So that is this vector Y. So what is A transpose A inverse? Can you tell me what is A transpose A inverse? You know what is matrix A? You know what is matrix A? What is A transpose A? It's going to be a scalar, right? It's going to be a scalar, is it not? Sorry, what is it?
Yes, sir, it will be 1 into 1 scalar.
It is 1 into 1 scalar. So what is that 1 into 1 scalar?
1.
N.
Capital N. It is capital
capital.
N, right? And the inverse will be 1 by N. So the inverse will be 1 by capital N into A transpose YD. So what is A transpose YD now? So A transpose, if you allow me, I can write down this A transpose as 1 capital N transpose. So what is 1 capital N transpose YD going to do?
Summation of all YD values.
Summation of all values in YD, right? So do you all agree that this is actually equal to average of the vector YD? Alpha 1 hat is actually the average of the vector YD. Is that okay?
Yes, sir.
Excellent. So if you have a constant model, if the model were to be constant, what is the least squares telling you to do? The least squares is telling you to take the average. So alpha 1 hat is average. So this is something like you have a data, you want to represent data with single point. What is the best point with which you will represent the data? The average of the data, right? That's what you would have said. That's what this least squares fit is basically telling you. But The best representation of data is average. That comes with the assumption that you are looking at mean square error, right? Root mean square error as your minimization. Okay. So if you calculate the root mean square, so if you have seen the lectures that I have already shared, then what is the root mean square error of this vector RD, the residual vector RD? You can see that this is actually the standard deviation of the vector YD. So the mean square error is actually the variance. So it is a very interesting interpretation of mean and variance that you have already seen in your second year probability statistics. So what is it? It is saying that if you have a data set and you want to represent the data set with a single point, then the best single point with which you can represent the data is the mean. And what is the error in the estimate? What is the error in representing the data set as a single point? The error is standard deviation. Okay, or the error square, sum of squares in the least squares is actually the variance. So this is a very beautiful interpretation of variance and mean for the given data, right? So this is something that is really very important. This is a beautiful interpretation of mean and variance. Okay, so if you have a constant model, then the interpretation of mean and variance, okay, interpretation of mean and variance. And mind you, if you instead of two norm, if you look at one norm, of RD as the measure of matching rather than two norm of RD, do you know what you will get as the alpha 1 hat?
Median.
Yeah, you will get median. Excellent. So you will get a median as the point representation of the data. Okay, so instead of least squares, if you use one norm data fitting, L1 data fitting rather than L2 or least squares data fitting, you get median. So this is something that is very interesting. Okay, so you have to understand this. So I thought this is a very beautiful thing to see. Okay, so that's what I wanted to bring to your notice. Okay, so another thing is a regression problem. So univariate functions. Okay, so univariate functions is what I will first focus on, and then from there we can go to the regression problem. So what is univariate functions? Univariate functions is the case when x is equal to n is equal to 1. So we had assumed that x is in Rn and y is in R, right? So instead of x is in Rn, suppose I have x also is in R and y is also is in R, right? So I have independent variable which is a variable in R instead of Rn. Is such a thing is called as univariate function, and then you can fit the straight line, right? So straight line fit. So in straight line fit, what will you do? In straight line fit, you have the data, so you will take the first basis function as 1 and the second basis function as x itself, right? So these are the two basis functions that you will have, and the model f hat x will then be equal to alpha 1 f1x plus alpha 2 f2x. So this will be equal to alpha 1 plus alpha 2x, right? So this is your model f hat x of the data, linear model, right? Straight line model. And if you have this straight line model, then what will be the matrix A that you will be looking at? The matrix A will be 1, 1, all 1, capital N number of times. And then the data points x1, x2 up to x capital N, right? So this is what you will have. And this is the matrix which will be Rn by 2, right? And the two parameters that you want to estimate, alpha 1, alpha 2. So the data is always x1 up to xn and y1 up to yn, right? So this is your A, and yd will be equal to y1 up to yn, correct? So this is what you will have, and then you can do A transpose A inverse, A transpose yd, and you get the parameters alpha 1 and alpha 2, right? So this is the straight line fit. Similar to this straight line fit, I can generalize and I can talk of polynomial fit, right? So this is something that you see, polynomial regression. So what is the polynomial fit? Again, I'll take n is equal to 1. I take n is equal to 1. And then the basis functions I take are f1x is equal to 1, f2x is equal to x, f3x is equal to x square. In general, fpx will be equal to x to the power p minus 1. and fp plus 1x will be equal to x to the power p, right? So these are the p plus 1 basis functions I take. These are actually the polynomials 1x, x square, so on and so forth, up to x to the power p, right? And what is the data that is given to me? The data that is given to me is x1, y1, the data pair, so on and so forth, up to x capital N, y capital N, right? N data points that are given to me. So can you tell me what will be the matrix A? How will it look like? What is the size of matrix A? So what is the first column of matrix A? It will be 1, all ones. Then what is the next column? You will have x1, x2, so on and so forth, up to x capital N, right? Then what is the third column? Square. So you will have x1 square, x2 square, so on and so forth, xn square. And what will be the last column? x1 to the p, x2 to the p, so on and so forth, xn to the p, right? So what
why
is
are we
this?
considering p plus 1 basis functions here instead of p?
No reason. I can have any number of basis functions, right? P is just a notation.
Sir, how actually are we deciding what the basis functions will be for like
That is based on your experience of working with that data set. It is your discretion what basis functions you choose. It is something that you have to decide. So as a person who is trying to build a model for the data, what is the model form that you choose is something that you have to decide, and that is something that you will realize is comes with experience. So there linear algebra cannot help. Once you decide what is the model form, then how to estimate, mathematics in general or linear algebra in particular can help. But how am I deciding 1x, x square, xp minus 1 xp? It's up to you. It's based on your experience. And that is the beauty in the subject. Like, how do you decide that? That's your beauty. So there are some ways in which you can decide, but we are not going to really look into that. So here, what is the size of this matrix A?
N cross
p plus 1.
N cross p plus 1. Okay, so this is the matrix that you have, and this matrix, because of its special structure, obviously 1 x1 square up to x1 to the power p, 1 x2 square x2 to the power p. This particular matrix is called as Vandermonde matrix. Okay, so there is a special name, Vandermonde matrix. Okay, so this is the name of this particular matrix, and you have the vector yd, obviously constructed from y's. Then you can estimate the parameters alpha 1, alpha 2 up to alpha p plus 1, and this is what we need. Okay, so that's what we have. So anybody who has taken regression course, have you seen these things before? Have you seen this before? Vandermonde matrix in polynomial regression. Have you seen this? So one of the things that I will ask you to check for these Vandermonde matrix and all is that this Vandermonde matrices typically are ill-conditioned matrices. Okay, so these are ill-conditioned matrices. Okay, so what is ill-conditioned matrix? You have to look at the condition number of this matrix. What is condition number? Condition number is maximum magnification divided by minimum magnification. Correct? So you look at maximum magnification by minimum magnification of A, and when you look at this, you will see that this is really very high. Okay, especially as you increase this P, you will see that there is a problem with condition number of these matrices. And that's why people generally avoid doing polynomial regression, because this matrix A is ill conditioned. If the matrix A is ill conditioned, then you know that there is going to be a problem, right? So there are various problems. So we'll look at these type of problems when we do sensitivity analysis of least squares problem. At that particular point, we'll come back and revisit, but you can check. And this is something that I think those who have done regression analysis would have already discussed in the class. Okay, so this is something that you can see. The other thing that people generally do is log transform of dependent variable. Okay, log transform of dependent variable. So what happens in log transform of dependent variable? So you have the dependent variable. Typically when y, the dependent variable is positive and has a very large range. Okay, positive and varies over a large range. So what people really do, because it is varying over large range and all the values are positive, what people do is they took log transform and they define a new variable w to be equal to log of y. Okay, and when you have w to be equal to log of y, then use least squares to develop a model for w. Okay, develop a model for w. Okay. So you have this w hat is equal to this model g hat into x, right? So you develop a model for w, which is g hat. And then how do you go back to the relationships with this thing? So y hat, they will compute as e to the power w hat, which is nothing but e to the power g hat x. So this is how they will compute y hat. Okay, so there are certain computational advantages, because range of y is really very big. You don't want to work with large range of y. Like y really varies between 1 to 1000, 1 to 1 lakh, say for example. That's how the variation in y is. So that variation is really very high. So this is what typically you will do. You will do the log transformation, and then you will try to build a linear model for the log. Okay, so that's what we do. And there are certain rules while you do the data fitting. So for example, I hope you all are aware, but I'll just mention these rules anyway. So typically when you build a model, the most important requirement of the model is generalization ability, right? So what is generalization ability? So what we really want out of the model is not only that it mimics the given data set, but it performs well for the data set which we have not seen during the training. So what is training? So the model parameters that you computed alpha 1, alpha 2, alpha n, those parameters learn their values from the data. What are the data points? x1, y1, x2, y2, xn, yn, right? So obviously the way we set up the cost function, the best values of the parameters are learned, right? So the data and the prediction y hat and y, they are actually matched as closely as possible because of the cost function that we set in the given data set. But that is not the only expectation out of the data set. Now you start seeing a data xi, which is not seen previously in the training phase. So it was not present when you had estimated the values of alpha 1, alpha 2, alpha p. Then your model should be able to predict reasonably well, at least as good as the training phase on this unseen data also. That is the generalization ability. Okay, so this is something that is really very important. So expectation generally is that this generalization ability of the model should be good, and there are certain probabilistic ways. So we'll assume that the given data comes from certain probability distribution. So if you make those assumptions, then we can talk of how good the generalization will be, but that is not in this particular scope of the course. But that is something that we have to understand. In order to kind of ensure generalization, what typically we do is that we divide the entire data set x1, y1, x2, y2 up to xn, yn. So this data set, typically what you will do is you will divide into two parts, train and test, right? So train and test. So you will keep some data. So you'll keep some data and you will pretend as if that data is a new data, right? And you will only work with the training data. So you can do like 80%, 20% divide. So you can randomly choose 80% of the observations or data points for training. So capital N, so that data that will participate in estimating the parameters alpha 1, alpha 2 up to alpha p is basically only the 80% of the data. And then you see how well the predictions work, how well the prediction works for the remaining 20% of the data set. Are they like somewhat similar to the training, like training matches, right? So this test error, you see, compare it with train error. And if those two test and train errors are reasonably similar, they're close to each other, then you say that model is doing well in generalization also. Or the model is not doing well in generalization, you have to change the model. So you have to add more basis functions or play around with that. So that is what basically you will do, right? So that is in part how you choose basis functions. If that's what Kaushik you meant, then this is something that you have to do. You have to play with the data. You have to see how good the generalization is for the given basis functions, and based on that come up with the model. Okay, so the restriction, the only restriction that we keep here is that the model is linear in parameters. Okay, that's the assumption. Once you have that linear in parameter assumption, then you can use the least squares model, right? So that is what we really are going to look at. So I think that's all I wanted to say about this data fitting. And if there is anything else that you have in mind, if you want to add, you can add now. Or in the next week, what we are going to do is we will do least squares classification basically. Okay, and once that least squares classification is done, then possibly constrained least squares is what we want to finish in next week, so that we can move further to these other decompositions like SVD and eigenvalue, eigenvector, and their application. That's what we will do. So, any comments? Anything that you would like to add? Yes.
Sir, in the van der Monte matrix,
Yeah.
if its condition number is too high, then for small perturbations in A matrix, the solutions will change a lot.
Possibly. They may or they may not, based on in which directions the perturbations are there. That's what I have to point out. But you are right. The parameters alpha 1, alpha 2 up to alpha p plus 1 that you will find out from the data, that they are more prone to the perturbations. Yeah, that's true. They are not robust to the perturbations, small perturbations in data. You are right.
Sir, so this is the interpretation from a sensitivity analysis point of view. And
Correct.
the same thing in machine learning people say as overfitting.
I don't think overfitting is really this. Like overfitting is basically when you have very good training performance but very bad testing performance. Is it not?
Yes, sir.
Yeah, I think if I understand correctly, then that is what overfitting is. Very good training performance, but very bad test performance, validation performance. That means that model is not performing well on the unseen data. That means that your model is very like highly trusting the only training data set. That's what your model is doing, right? So that is overfitting, if I understand correctly. What you are having is the variation in parameter values for small perturbation in data. The variation in parameter values may still not affect greatly the perturbation, the predictions. What you are really interested in understanding overfitting is prediction performance, right? So there are two things. There is one thing which is variation in the parameters, variations in alpha 1, alpha 2, alpha p plus 1, and how do those variations affect the predictions y. So we have not yet understood how these variations in alpha 1, alpha 2, alpha p plus 1 affect the prediction performance. So that study also is done, it's well understood, but we have not done that in this course.
And what is that study called?
And so this is done in a standard regression course. So if you see any standard regression book, in the regression book, this will be done very nicely. So any standard regression course that you take actually talks of all these things. So only reason I am not going to talk about that is because I have not laid out the like distributions, like normal density and all that. I have not talked about it. So that's why I'm not really going to go into that direction. Is that okay, Ashraf? Does that? Yeah, okay.
Yes, sir. Yes, sir. Thank you.
Sir, did we incorporate the error in the data so far in our analysis?
No, we have not. So this is the data that is given to us, x1. So y may come with corruption. So this y d that you see here, so the vector yd that we constructed, so y1, y2, yn, that data I had, it may be corrupted by noise. That's fine. But I am going to only look at what is the value given to me at this point of time. That's all. So when you start doing regression analysis, then you will say that you will see what is the noise characteristic, and based on that noise characteristic, then what will be the distribution of alpha 1, alpha 2, up to alpha p plus 1, the parameters that you will estimate. So those things will start coming into regression analysis that I am not really going to do. So that's why I'm not really worried about what is the error in y1. So this y1 encircled might be corrupted by noise already, but I'll take that value as is in the estimation as I do anyway. So we are more focused onto the linear algebra part of this, not the statistics part of this. So that's why I'm not really going to talk about the noise characteristics. But there are noise, there are data the values are corrupted for sure. So this y1, y2, yn values that you see, they are like corrupted by noise. That is the. Is that fine?
Yes, sir.
Okay.
Sir, one question.
Yes. Please go on.
So kind of a basic question, sir. But like the rows, the columns of matrix A are linearly independent. That's fine. And as you said, the features should not be a linear combination of features.
Correct. Correct.
But that takes us to the point that how do we find that? I mean, in a practical life, how do we find that the columns are linearly independent? And that takes us back to the discussion where you showed in the previous class, few classes back, where the probability of the columns being linearly dependent is very minimal. It's like in the XY plane, it's just like two lines, two intersecting lines passing through the origin.
Yeah. So yeah, you are right. You are right. Yeah. I follow what you are saying.
Yes, sir. So I'm thinking like but in reality, if you have to figure out that a feature is dependent on another feature, then what is the way? Do we do a regression of that feature on another feature? Is that the only way out, or is there any other mathematically affordable way to figure that out?
So what you have to look at is basically will become clear when we do singular value decomposition. So what you really have to do is you basically look at the condition number of the matrix A, and based on the condition number of the matrix A, you know how good or how bad the features are as far as the linear redundancy amongst themselves is concerned. Okay. So if one feature is linearly deducible from the other features because of all the noise, like what just now was asked, like Ravi asked, are x and y values corrupted by noise? Obviously x and y values are corrupted by noise. If x and y values are corrupted by noise, then the columns of A are also corrupted by noise. So to start with, the features were linearly dependent. Because of noise, the two columns become linearly independent, but they are almost linearly dependent. In such a situation, what do we do? So like we had discussion in last class about condition number of the matrix. What is condition number? Very high condition number really telling us. A very high condition number basically is really telling us that the columns are almost linearly dependent. So if the columns are almost linearly dependent, what does that mean? That means that one feature can almost entirely, like almost correctly be deduced from the remaining features, like as a linear combination. So we decide which feature, so what linear combinations to take, and what do we do in such a case so that there is no problem of this linear redundancy, how to get rid of that. So these are some questions that will become clear when we study singular value decomposition. So when we study that, basically singular value decomposition, principal, component analysis, everything basically takes us to that. So what we are really doing is that we want to reduce the dimension. So to speak, the feature dimension needs to be reduced because there is redundancy in feature space. So if F1, F2, Fp, if you call them features, then that F1, F2, Fp, the features have redundancy amongst themselves. So you want to sort of go down. So you want to reduce the number of features. So that is the dimensionality reduction problem that we are talking about. So that actually is very well understood through singular value decomposition or principal component analysis. So we'll come to that. But your question is right. And in general, you are always right that these features will be always linearly independent as far as linear algebra is concerned. But like there is they're almost linearly dependent. That's what you can say. And if they're almost linearly dependent, then how to quantify that almost linear dependence? So all those quantifications will come through the singular value decomposition or principal component analysis. Both are actually the same things. We'll learn that when we will.
Sir, and this is the same as the multicollinearity analysis that we do?
Yes,
Or?
yes.
Okay.
So what I was just talking about is exactly the multicollinearity analysis. You're right. Okay, I guess in that case, if no further doubt, we can stop here. We'll meet next week and we'll continue this discussion. So next week, mainly what we are going to do is least square classification and constrained least squares problem. Okay, so that's what we really want to look at. And once this is done, then we'll move on to the next topics of like singular value decomposition, eigenvalue, eigenvector decomposition, and like this multicollinearity issue of features. Possibly page ranking algorithm, that is the eigenvalue eigenvector decomposition application. And I have in mind to cover a very interesting problem. If there is time, I will cover. It's called as inverse eigenvalue problem. Okay, so that is something that I will really like to discuss. It has like wonderful applications in some areas. Okay, so I'll try to do that as well. So let us see if there is enough time to do it. Okay, then I guess this is it for today. Thank you very much. See you next week.
Thank you.
Thank you, sir.
Thank you.